All right, so half-life. So when a nucleus breaks down and decays, depending on which element it is, that happens at different rates. So sort of how quickly these nuclei break down, we call that the decay rate. The number of nuclei that will break down per second. And this decay rate depends on what type of element it is. Some elements decay quickly, some decay slowly. So the term we're usually going to use to indicate how quickly a nucleus of an element will decay is called its half-life. The half-life of an element is how long it will take for half of the nuclei in the sample to break down, to decay. If you look at this diagram on the bottom, at the start, we have all of the sample is what we call the parent isotope, the original starting nucleus. After one half-life has gone by, how many of these nuclei do you think will have decayed?
Half of them.
Half of them. Okay? So then what does that mean after two half-lives?
It's a full 3/4.
No.
3/4?
Should they all be gone?
No.
No. Because in the next half-life, half of the remaining parent isotope will decay. So you'll still have some left. So right now, in this, after two half-lives, there's about 8 nuclei left of the parent isotope. How many will be left after another half-life?
4.
4.
And 2.
And then 2.
And 1. 10.05.
So, this sort of shows the same idea. Shows that half of the nuclei are decaying in each half-life until eventually you have enough. So different elements have different lengths of their half-life. Some decay more quickly than others. So here are some examples of common radioactive elements. Carbon-14. Carbon-14 decays into nitrogen-14, has a half-life of about 6,000 years. Potassium-40 decays into argon-40, 1.3 billion years.
Just for one half.
Uranium-238, does this look familiar?
Yeah.
That's the decay chain you guys just worked out. Uranium-238 decays into lead-206, about 4.5 billion years.
Guys, we're so good.
And rubidium
10 minutes.
decomposes into strontium in about 49
Oh my god.
billion years.
That's not bad much.
I'm not right now.
It's not that much at all.
And we live for an average
Now,
8
these
years.
half-lives, this means that elements decay at a predictable rate. And so we can use half-life to determine how old something is, if we know how long it takes for half of it to decay. For example, if we look at this chart here, talking about carbon-14. And carbon-14 is a half-life of about 6,000 years. So at 0 half-lives, it's all carbon-14. After 1 half-life, it's only half carbon-14. Do you remember what the other half would be? Nitrogen-14. And it will have taken about 6,000 years. After 2 half-lives, a quarter of the original carbon-14 is left. And it will have been 12,000. And repeat it over and over again. What's next? After 4 half-lives, how much of the original is left? 116. And how many years will it have been? 24,000 years. After 5 half-lives, you'll be left with 1/32 of the original. It will have been 30,000 years, and so forth. You can repeat this over and over.
Ours stops at 161.
That's fine. So we can look at the ratio of the parent isotope to the daughter isotope and use that ratio to estimate how old a substance is. So, what percent of the original C14 remains after 2 half-lives? 1/4. 25%. How about 3 half-lives?
0.125%.
No.
1/8.
1/8 or
0.325.
Yeah.
12.5%.
I knew that.
Oh, duh.
So, as the decay product increases, what happens to the amount of the original isotope? It decreases. All right. So if I have a 1,000 gram sample, a kilogram of carbon-14, okay? I have a kilogram. After 6,000 years, 500 grams will be left as carbon-14. After 12,000 years, 250 grams would be left. And repeat it. After 30,000 years, how many half-lives will have gone by?
5.
And how much will be left?
31.25 grams.
What would the rest of it be?
Nitrogen 14.
The rest of the sample would be nitrogen 14, because that's what carbon-14 decays into. So a scientist had a 100 kilogram sample of our curium, the strongest and most beautiful element known.
I thought Frankfurt was.
Too bad it's
Wait,
made
is that
up.
an actual element?
The half-life of our curium is 100 years. How much our curium would be left in 200 years? So how do we figure this out? Colin?
So since we have an 100 kilogram
Yep.
sample and the half-life is 100 years, after 100 years it would turn into 50 kilograms.
Yep.
And then after 200 years it would, because it was half of 50, so it would be 25 kilograms.
Correct. We started with 100 kilograms. After 100 years, we will be left with 50 kilograms of our curium. And after another 100 years, we'll be left with 25 kilograms of our curium.
Oof.
Does that make sense? A 200 gram sample has a half-life of 50 days. How long will it take for the sample to decay to 25 grams? Now we're asking a little different. We start with 200 grams. When will it get to 25 grams? Well, we start with 200. What's it going to be after a single half-life?
100 grams.
Then
50.
50 grams,
25.
then 25 grams. So how long will it take to get to that?
150 days.
150 days, 3 half-lives.
Are there any actual elements that have that short of a half-life?
Yeah, some are only a few minutes.
How is
All
it
right.
Then how is it possible that scientists have found,
Observed them?
Yeah, observed them. Do they like isolate them so they can't decay, or do they just always decay?
No, they're always, and it's random, so you can never actually predict when a single atom will decay. Sort of a probability. Just like we know the probability of flipping a coin and getting heads is what?
50%.
But you can never predict with certainty an individual flip of a coin. You never know what it's going to be. Well, I do, but
Unless you look.
it's true.
When am I gonna get my unless it's a magical coin.
I can predict with great accuracy.
Unless you dropped it, unless you flipped it into a